it later. All right, so one last problem on quadratic surfaces. I want to share my screen. I'm going to use a example, hopefully. This one. And I'm trying to get it up still. If you have your microphone, I'll make sure you turn it off. There we go. Hopefully that's got it. Here's the screen I want to share. It comes out of the homework. This quadratic surface, can you find the equation for it, right? Last time we said, here's some characteristics, find the equation. How can we do this one? Well, you look at it, and the first thing to do is look what it looks like. It looks like a hyperboloid of one sheet, right? You just have to memorize those 6 different figures. This looks kind of like a spool. And what's more, it's in the standard orientation, opening about the z-axis. So I know immediately how to write down the general equation for it. Since it's centered at the origin with opening around the z-axis, there's a standard equation for that. Now I just have to match it to these parameters. At its waistline here, the ellipse at its center, its semi-axes are 4 in the x direction and 6 in the y direction. And up here, at z equals 9, we've got a semi-axis 8 and a semi-axis 12. Let me put this back on the whiteboard here. And here it is, not as brilliant, but hopefully readable. X, Y, Z. And a height of 9. And a height of 0. These are 6 and 4. So the first thing to do is say, that looks like a hyperboloid of one sheet. Given it's a quadratic surface, that's the only thing it can be. I can immediately write the equation. Again, your book writes it, with terms on opposite sides a little bit from what I do, but I like to write so I can remember from the ellipsoid equation, minus x squared over a squared, minus y squared over b squared, plus z squared over c squared. The ellipsoid equation with 2 minuses equals 1. And if you leave the z positive, oops, I did the wrong one there. One sheet. X squared over a squared plus y squared over b squared minus c squared over c squared equals 1. Hyperboloid of one sheet is 1 minus. That's why I do it that way. Now, what do I find these are? You can look and see that there's a trace. Z equals a constant 0, right? That's what you get. This ellipse here. By intersecting with this with the plane z equals 0, you get this ellipse with semi-axes 6 and 4. Since I know this is an ellipse, how do I know that it's a quadratic surface and the only one it can be is a hyperboloid of one sheet and it has elliptical cross sections? Since it's an ellipse, I know that it's 4, z equals 0. I can plug z equals 0 into this equation and get x squared over a squared plus y squared over b squared equals 1 is the trace in this z equals 0 plane, right? Now, since this is obviously an ellipse, and I can see the semi-axes are 4 and 6, I say for this trace, therefore, A equals 4 and B equals 6 to match the semi-axes there. Now what I have, a hyperboloid of one sheet, right? This is an intermediate step, is x squared over 4 squared plus y squared over 6 squared minus z squared over what we don't know, c squared equals 1. What can c squared be? I have to have some more information. Well, I do. I can go up actually to either one of these points. I observe something that's 9 units up, and it's over the y-axis. It must be the point x equals 0. y equals 12, z equals 9, right? So I can plug that point in there, or I can plug this one in. 8, 0, 12, 12 units up, 8 units out in the x direction. Claim y equals 0. If I plug this in, make it satisfy the equation, then I have 0 squared over 4 squared, that's easy. 0. Plus 12 squared over 6 squared, 4. Minus z squared over c squared equals 1. I can solve for c squared out of that, right? I get from that 3 by subtracting 1 over equals z squared over c squared by adding z squared over c squared to the other side. Oh, and then wait a minute, z is 9. Put that in time. Put it in this last step, I guess. I'm 9 squared over c squared. Well, I have this equation. 3 is 9 squared over c squared. So it implies my reciprocal 1/3 is c squared over 9 squared, 81. So c squared equals 27, right? 81 over 3. C is 3 square root of 3, or 27. Now I've got it. So with this, just arrow this way, plugged in, I now have x squared over 4 squared plus y squared over 6 squared minus z squared over 3 square root of 3 squared equals 1. I think WebAssign takes it this way. If you want to put it in the same notation they do, I think some of them force you. They'll put x over 4 quantity squared, y over 6 quantity squared, z over 3 square root of 3 quantity squared here. So we'll write it in the book's notation. So you can check it on WebAssign, make sure it works. All right, so there is an example of looking at a picture and being able to figure out what the equation of the quadratic surface is. That being said, all these things are subject to translations just like the conic sections were. If you want to move these, you just replace x by x minus x0, y by y minus y0, z by z minus z0. And that keeps them the same shape, just with their center moved to x0, y0, z0. So let's just make that one last drawing point here, even though it's not on the homework. I think it's an important point. And I might get that to you in an extra credit problem or something, even though it's not on the department homework list. To take one of these things that's not centered at the origin and plot it for me. In fact, I think I've got one on the practice test here. Let's do this one. Suppose I wanted to sketch the graph of x squared minus 4x plus y squared plus 4z squared equals 0. What could that be? This isn't on the homework set, but like I said, I'm going to ask you this pretty soon. What could that be? Here's what you can do with these that have squared terms and some unsquared terms. You can complete the square. If you write this equivalently as 1 times x squared and factor the 1 out of both these terms, I just do this in case there's something besides 1 here in the future, minus 4x plus y squared, 1 times y squared if you like, plus 4z squared equals 0. Like that. And the object is to make a perfect square in here, all right? What do I need to make a perfect square? You remember how to do this from algebra. You take 1/2 of this number and you square it. 1/2 of -4 squared is -2 squared is 4. So I need to add 4 in here to make this a square. And to balance the equation, I then need to add 4 times 1 to the other side, 4. Now I can rewrite this equivalently as x minus 2 squared, that's what square this is, right? It's always x minus 1/2 of this number, or plus 1/2 of whatever the number here squared, plus y squared plus 4z squared equals 4. And if I divide this through, you get 1 on the right-hand side. Observe a quadratic surface in its standard form, just translated. Here it is, y by 4. I've got x minus 2 squared over 2 squared, plus y squared over 2 squared, plus z squared over 1 squared equals 1. There it is. Evidently, this is an ellipsoid. This has got the standard form. If I just didn't have this minus 2 here, right? X squared over 2 squared plus y squared over 2 squared plus z squared over 1 squared. With semi-axes 2, 2, and 1. So you actually get circular cross-sections in the xy plane and parallel to the xy plane, but elliptical cross-sections in the other directions. Ellipsoid with A equals to B equals to C equals 1 in the standard equation. Shifted, if you replace x by x minus 2, that moves the center from 0, 0, 0 to 2, 0, 0. You can also shift the other ones. I didn't bother in this problem, but you can complete the square in all three variables. Get those first power terms out of here and put these things into these standard forms shifted. Just replace each of the variables by the variable minus a number. All right. And so that one sketches like this. I just come out 2 units on the x-axis. Make semi-axes 2, 2, and 1. So I go back 2 in this direction. It's actually circled in the xy plane. And then, but it's an ellipse 1 unit higher in the z direction. So it looks like that. Almost, huh? Anyway, there's the ellipsoid centered to semi-axes 2. That'll finish that section. There is more we can do on it. There's some places for the exam. It's on different coordinate systems. What you find out when you go on to apply these things in the sciences is that frequently the equations become very complicated. But there's some symmetry in them. Like there's a radial symmetry. Gravity is symmetric, right? It pushes at the same force if you're the same distance away. So along any sphere around the origin, gravity has the same magnitude, right? This is the same strength from the same distance. That suggests if it's got a spherical symmetry, we got to use spherical coordinates. So here's some coordinate systems. This is the handout I've generated here. Find it. There it is. So you see in this one, 2 different coordinate systems actually. Both of them are very useful. Why are they useful? Because lots of things in nature and in devices that people make have some sort of cylindrical or spherical symmetry. We make cylindrical and spherical coordinates. There are other coordinate systems. There's parabolic and hyperbolic coordinate systems, for instance. They're 2 popular ones, and they're used sometimes in certain applications. But these are the most used. And so here's what you do. Any point, I'll move my cursor up here, can be identified in 3 space by dropping a perpendicular to the x-axis and calling that the x-coordinate, dropping a perpendicular to the y-axis and calling that the y-coordinate, dropping a perpendicular to the z-axis and calling it the z-coordinate, and then identifying that point by x, y, z, the 3 coordinates when you drop perpendiculars, right? Euclid said there's a unique perpendicular to each from a point to a line that's not containing the point. But there's another way to do it that lends easier equations when you have a cylindrical symmetry, and that's this right here. You, instead of dropping a perpendicular to each axis, drop a perpendicular to the xy plane. All that coordinate z, same as before, right? It's the same height above this xy plane as if you used xyz coordinates. But now take this line segment from there back to the origin and say that has length r. And then this line segment back to the origin, take the angle counterclockwise, right, in standard position from the positive x-axis to this line segment, call that theta. And those three numbers are the distance of the projection from the origin, the angle theta in standard position to that line segment to the projection, and z, the height above the xy plane, also makes an ordered triple that identifies points. Each r theta z, in fact, identifies exactly one point. You can imagine it, right? You turn through this angle theta, you go out a distance r, and then you go up a distance z. There's only one point you can go to, intuitively at least. The equations prove it, actually. We'll put the equations up shortly. But that's called cylindrical coordinates because there's a cylindrical symmetry. If you were to put r equal a fixed number, r equal 1, for instance, what would happen? You get all points at 1 unit from the origin here. Suppose r is 1. You get all points at 1 unit out, which means you could go around in a whole circle and you could go up arbitrarily high. You get a can shape, right? A right circular cylinder. So when you put r equal a constant, it gives you a constant capital R or something. Then it gives you a right circular cylinder of radius capital R going up to infinity down to minus infinity. So hence cylindrical coordinates. If you put theta equals z equals a constant, you get other things too. Like z equals a constant is still a plane, just like in xy coordinates. So that'll be cylindrical coordinates, and then these will be spherical coordinates. We'll talk about those in a second. All right, so here's cylindrical coordinates. So the picture is better than I can draw. Any point in three-dimensional Euclidean space, drop a perpendicular to the xy plane, take a line segment back to the origin, call that distance r, take the angle in standard position to that line segment, call it theta, take the height above the xy plane, call it z. And now we can identify any point we want as r theta z. Now I said each r theta z yields only one coordinate, but in fact, there's an infinite number of ordered triples r theta z that identify one point. So you could also take any point out here that has coordinates r theta z. If you add 2 pi to theta, then it's the same direction, right? Because it's just one rotation more. Or add 2 times 2 pi, or minus 5 times 2 pi, right? You can add any multiple 2 pi to theta, and it still takes to the same point. So even though each ordered triple only identifies one point, there are an infinite number of ordered triples that identify the same point. Furthermore, if you take a point on the z-axis, then it doesn't matter what theta is, right? Whatever you rotate around to, if r is 0, right, then you'll be on the z-axis no matter what theta is. So then theta is arbitrary, and you can just put r equals 0, theta equals anything, and z is whatever the length of the increment is along the z-axis. Identifies the same point. So there's an infinite number of ways of identifying these where you put any real number for theta. And then finally, the origin. Same thing. If r equals 0, theta can be arbitrary. Just z has to be 0. So all the points on the z-axis have many ways to. You can use any angle you want. All right, and so r theta z is going to identify each point. What are the equations of the transformation for this? Here's the transformation. If I want to find what the x-coordinate is, given these cylindrical coordinates, r theta z, I just drop a perpendicular down to the x-axis, and I say, well, from this triangle, it's a right triangle. X, this side here is, well, let's see, x over r is the cosine of theta, right? It's x over hypotenuse. So cosine theta equals x over r. Tells me I'm multiplying by r, that x equals r cosine theta, right? So that's how I get x given r, theta, and z. Similarly, over here, the y coordinate. That's this side. Y over r is opposite over hypotenuse, has to be the sine of theta. Multiply through by r, and you get y equals r sine theta. Then z is just the usual coordinate. You put z equals z. There's the conversion to cylindrical coordinates, or from cylindrical coordinates to x, y, z Cartesian coordinates, also called rectangular coordinates. Wait a minute. That looks really familiar, doesn't it? That's just polar coordinates add z. That's the way to think of these. They're polar coordinates add z. And that's true with one small exception. In polar coordinates, we used to allow r to be negative. Now we're going to restrict r to be non-negative. It turns out there's some problems with integration in 3 dimensions. R can switch from positive to negative. There's some singularities that make the integrals rather intractable. So since we can sweep out all points without letting r be negative, in cylindrical coordinates we restrict r to be non-negative. So that's the restriction. R is greater or equal to 0 in this. And then we can go the other direction. What is the inverse transformation? We might notice that r by the Pythagorean theorem is the hypotenuse is the root sum square of these two sides. R must be the square root of x squared plus y squared. Slightly different than you wrote in polar coordinates, right? Although the book doesn't emphasize that. In polar coordinates, most generally, we write r squared equals x squared plus y squared. And r can be either plus or minus the square root, right? And if you make r minus the square root, then you have to take theta the opposite direction, and with r negative, go out the absolute value of r the opposite direction. So that's how we did polar coordinates, just to remind you when r was negative. And you wrote this transformation, you let r be positive or negative, and then theta, well, let's see, tangent of theta is opposite over adjacent is y over x. So let's write it this way, tangent theta is y over x. And then, of course, z equals z. Back. There's the transformations the other direction. However, there's a hitch here, right? And for any tangent theta equals a number, there are 2 solutions, unless it's 0, unless you're at the origin. That's assuming there actually is an angle there. If you take tangent equal a number, there's 2 solutions, right? The angles in opposite directions have the same solution. Remember that from trigonometry? In trigonometry, you take this circle and you say, oh, any point x, y is the cosine and the sine on the unit circle. That's all. That's theta. And if I put theta plus pi, well, look, the coordinates are minus. If this is x0, y0, this is minus x0, minus y0. But their ratio, tangent theta, is y0 over x0 from this one is the same as minus y0 over minus x0 is the tangent of theta plus pi. So angles opposite each other have the same tangent because the ratio y to x is the same number. So this one has to be appended saying, since we're making r non-negative, we're going to require theta to be the same quadrant as the original xy was. Theta in the same quadrant. If we were letting r be negative in polar coordinates, then we might have to make it the opposite quadrant. That's the only issue. Converting from cylindrical to rectangular is easy. You just plug the numbers in and see what x, y, and z are. Converting back this way, 2 of them are easy, but tangent theta, you have to figure out the quadrant. And what that means is this. When you go to compute theta from this formula, theta might be the tangent of y over x, but it's not always, right? The arctangent is one angle whose tangent is this number. The other one is the opposite direction, right? Pi units bigger. So it could be arctangent y over x. Arctangent always gives you a number, remember, between plus and minus 90 degrees. And so this is for theta in quadrant 1 or quadrant 4. This is only quadrant 1 or quadrant 4. But if your point is in quadrant 2 for quadrant 3 in the xy plane, ignoring z. Then you want the opposite end, which is arctangent y over x at 180 degrees, pi radians. We'll do this in radians. It's better for calculations later. So this would be theta in quadrants 2 and 3. And that's what you do. You calculate the arctangent, and then you add pi if it's supposed to be in quadrant 2 or 3. Now, this doesn't make it between 0 and 2 pi radians. It makes it between minus pi over 2 and pi over 2. And not even that, minus pi over 2 and 3 pi over 2. So you may want to rearrange this so it's between 0 and 2 pi or minus pi and pi or something standard. But you don't have to. It's the same theta. It will give you the right point. Regardless, you can add 2 pi to either of these and get the same point, in fact, is what we said. So it doesn't matter if you add 2 pi in any case. Now, if it's on an axis, right, these are between the axes. On any axis, it's obvious what the angle is. We can write those down, right? If y is 0 and x is positive, then it's 0. If y is 0 and x is negative, then you're going along this axis, and it's pi radians. If x is 0 and y is positive, it's pi over 2, and right, and that kind of thing. So you can figure the angle from which coordinate is 0 when it's on an axis. Just for your education, I'm going to add one more thing and say there's an additional thing in programming. If you program in MATLAB or C++ or any of those computing languages these days, there's a command that will do this for you always. As long as x and y aren't both 0, in which case there isn't an angle, we can say theta is equal to the a tan 2 function y followed by x. Now, I put the y argument first. I guess because they're thinking of y over x, right? But I don't know how it got that way. I'm guessing. But the a tan 2 function will always give you the angle theta between minus pi over 2 and pi over 2. So it won't give you exactly that calculation. This is between, minus pi and pi. This calculation gives me minus pi over 2 and 3 pi over 2, which is awkward, but it's easy to write down. This program will rearrange that slightly, and it will give you whatever the angle is between minus pi and pi. All right? Now, that being said, really what's most important is that you be able to do this when theta is a special angle, right? A multiple of 30 degrees or 45 degrees. You want to be able to do this exactly. So bear that in mind. And in that case, you may not want to do either of these calculations. You figure it out on the unit circle. So for special angles, use the unit circle. There's the whole trouble. It's just that nasty angle theta, right? For special angles, you can use the unit circle. If anybody's ever seen complex variables before, I don't know. This a tan 2 is the same as the arg function, arg, in complex variables with if y is the imaginary part of the number and x is the real part of the number. So this actually is a fairly standard usage in higher mathematics as well as in the computers. Just there it's called arg. All right. See if I can erase this. The problem with this board is when I leave it sitting too long, I can't erase it anymore. It provides you some comic relief here every time I have to erase it. Any questions at all? I hope that's fairly clear. All I did now is to use these equations. I'll star these. You want to memorize both of these and just say, wait a minute, I already know how to do this. This is polar coordinates add z, and this is polar coordinates add z. I just don't let r be negative anymore. So that's all you have to do on these problems. It's very easy, and I won't spend a lot of time on it. I want to get the spherical coordinates that are slightly more exotic, but we have to introduce these. Plus, maybe some of you don't remember polar coordinates real well. Suppose I said convert the cylindrical coordinate 4 pi over 3. This is number 1 on the homework, by the way, with my numbers. Minus 5 to rectangular Cartesian coordinates. How can I do that? Right? easy. Remember we said to go from cylindrical to Cartesian, it's just plug and chug, just plug them in. So, right, what always happens is you interpret the first one is R, the second one is theta, the last one is phi, just like you put X, Y, Z in that order. So X is going to be 4 cosine pi over 3. Y is going to be R sine theta is 4 sine pi over 3. And Z just carries across. Z equals -5. Now I said when you get a special angle, multiple of pi over 6 or pi over 4, then you want to do it exactly. Well, pi over 3 is a multiple of pi over 6, so I figured out on the unit circle. Remember trigonometry. Here's pi over 3 is a 60-degree angle. I got the perpendicular. I get the special triangle. Square root 3 over 2, a half. So the sine is the y coordinate. Square root 3 over 2. And the cosine is the x coordinate, 1/2. So this is equal to 4 square root 3 over 2. 4 times a half. The x coordinate is a half. Is 2. This is 4 times square root 3 over 2. Is 2 square root 3. Z carries across to 5. And observe that I have my cylindrical coordinates in order triple. Sorry if I'm repeating. I can't remember which class I told, but 3 dots means therefore in mathematics. Therefore, my coordinates are 2, 2 square root 3, and -5. Right? So polar coordinates plus Z for that. And the other direction is the hard one. So I leave these up there. And now I want to find rectangular coordinates. Or from rectangular coordinates. Which are 3, I'm sorry, -3, square root 3, 5, to cylindrical coordinates. Well, I'm going to convert the other way. Right? R and Z are easy. R is just the root sum square of x and y. So R is square root -3 squared plus square root 3 squared is square root 12 is 2 square root 3. Right? Now I observe that tangent theta is equal to y over x. Square root 3 over -3. Your calculator, depending if you got one of the computer calculators, can actually do the arctangent of this, but you'll get the wrong quadrant in this problem. Yeah, you get the wrong quadrant in this problem. So I'm going to do this. I'm going to rewrite this by taking the root sum square of these numbers. Let's rewrite it. Let's take the root sum square. Square root of -3 squared plus square root 3 squared. We just did it above, but is 2 square root 3. And I'll divide top and bottom by that number, and the top one becomes a half, and the top one becomes minus square root 3 over 2. Why would I divide by on the top and the bottom so I don't change the quotient? By this number. If I divide by the root sum square of these two numbers, then this squared plus this squared will now be equal to 1. It's a point on the unit circle. So this might be sine of theta. And this might be cosine theta. But what's another possibility? There's one more, right? You get the same ratio if you take minus this over minus this. So it could be minus 1/2 over plus square root 3 over 2. That has the same ratio. You just have to ask yourself, is this sine theta and this cosine theta, or is this sine and this cosine? It goes by the quadrant, right? The original point, I look at it, x is negative, y is positive, so it's in quadrant 2. In quadrant 2, I want this one, x negative cosine and y positive this one. So I scratch out this one because this will actually be in quadrant 4. And I want quadrant 2. Apparently this is the sine and this is the cosine, and now I can figure on the unit circle what that angle is. Once I divide through by this root sum square, if it's not a special angle, I won't see numbers I recognize. But here I recognize off the unit circle. Y is a half. X is minus square root 3 over 2. On the unit circle is be this point right here. Right? But since this is a 30, 60, 90 triangle, this is 30 degrees or pi over 6. The angle in standard position that gets me there is 5 pi over 6, right? Pi is a straight angle, back up pi over 6. Evidently, what you do is you write this tangent, divide through by the root sum square plus or minus to get the right quadrant. Interpret the top one as the sine and the bottom one as the cosine. There are other ways to do this, and again, you can do it on your calculator as long as you know how to add pi to get in the right quadrant. But you should be able to picture this in your mind after a while. So evidently theta equals 5 pi over 6. R we already computed is 2 square root 3, and z is just the number shown. Z equals 5. So I have now therefore cylindrical coordinates are, let's see, 2 square root 3, 5 pi over 6. Put R first, then theta, then z, 5. Minus 5, I'm sorry, minus 5. Or z equals 5, it should be minus 5. Okay, so there's both ways with cylindrical coordinates. All right, now we want to try and introduce spherical coordinates. So here's the spherical coordinate. Now what you do is you do just like you did at the start with cylindrical coordinates. You drop a perpendicular to the xy plane. But instead of calling that z, you just now can, and you still continue the line segment back to the origin. And now what you're interested in, what's the distance from the origin to the actual point itself? We call that rho. Rho will be the distance from the origin to the point, not to the projection of the point like it was over here. Right? Then angle theta is the same as before. We look at this projected line segment, the angle in standard position, counterclockwise to it, call that theta. And you can add 2 pi to its same direction, or 4 pi, or 6 pi, or subtract a multiple of 2 pi. Then the third coordinate is to take this line segment from the origin out to the point and take the angle phi down to it from the positive z-axis. And we restrict phi to be between 0 and pi because if we go past pi, it's going to run over the other side, the back octants over there, and then we'll have different theta corresponding to the same phi. To avoid ambiguity, we'll restrict theta to be between, or phi to be between 0 and pi. But we will allow theta to be arbitrary because it doesn't hurt anything like it does in the integrations with phi. So there's the 3 coordinates. Distance from the origin, rho, angle in standard position to the projected line segment, theta, angle from the z-axis down to the line segment to the point, phi. Any questions on that one? I hope that looks reasonable. So what are the equations for spherical coordinates? One thing you'll find that is nice about these, actually, these coordinate systems are very amenable to doing analysis with the quadratic surfaces and conic sections that we've been doing. They have easy equations. It's surprising you think these exotic coordinate systems maybe The equations look really complicated, but quadratic surfaces have fairly easy equations in cylindrical and spherical coordinates if they're put in their standard positions like they were anyway. All right, so here's the picture we said. Rho, the distance from the origin, drop the perpendicular down, theta the angle of the xy plane, phi is the angle down, and what we have now is that rho is the distance from the origin to this point. By the distance formula, it's the square root of the difference in the x-coordinates, difference in the coordinates squared, right? X, Y, Z, and 0, 0, 0. The distance formula says you have x minus 0 squared plus y minus 0 squared plus z minus 0 squared. Square root is the distance from the origin to x, y, z. Or it's just rho equals square root of x squared plus y squared plus z squared. It looks like r squared, rho, r from polar coordinates, just with one more variable. That's exactly what it is, right? So rho is easy to compute just like that. It's the root sum square of the x, y, and z coordinates. How about theta? Oh, that's easy too, because it's the same theta as in cylindrical coordinates. So you say it's the same. So you just write tangent theta equals y over x, where you restrict it to be in the same quadrant. Then it's the same calculation. How about z? Now z is a little more exotic. If I drop this perpendicular back to the z-axis and make a right triangle, I have this angle phi here, and I have z on the side, and I have rho on this side. I notice that there's phi. The cosine of phi is z over rho, right? So on this triangle, I notice that cosine z, cosine phi, is z over rho. If I multiply that by rho, I find that z, I'm sorry, if I take the inverse cosine, I find that phi is the inverse cosine of z over rho. Here's your conversion equations from x, y, z to rho theta phi. Or instead of putting root x squared plus y squared plus z squared here, I just wrote rho since you presumably already calculated it up there. But you can put in x, y, z and get rho theta phi this way every time. So there's the conversion in one direction. Now we want to do the other direction, right? Invert it and find rectangular from spherical coordinates. How do we find those? And we'll have to finish, we'll do the interesting examples next time. Make sure you get on next time. The examples will be harder. Well, you look at this triangle here. You drop this perpendicular and you say, this is x. I know this side right here. That's r from polar coordinates. It's the, from this triangle here. Well, this is r also. From this triangle here, it's rho sine phi. Right? This is rho sine phi, so that this over this is sine phi. So r here is rho sine phi. And then, that's the hypotenuse of this right triangle. So this side, the hypotenuse times the cosine. Right? So that this over this is cosine. And this side here, y, is the hypotenuse rho sine phi times the sine of this angle, theta. There it is. There's our conversion equation. We'll get x equals rho cosine theta sine phi. Y equals rho sine theta sine phi. And then up here, cosine phi is z over rho. Multiply that by rho, and you get z equals rho cosine. And this way is the easy way. Spherical to rectangular, you just plug them in and see what you get. So next time we'll convert some coordinates and we'll convert some equations. The homework won't be due until at least Saturday. Take a look at it and then see if you have any questions for next time. Any last second questions? All right, lots of stuff. I think it's not too hard today. Try that out. There.